Thank you, Hannah, for the introduction. Let me thank the organizers, also higher for the SPICE in general, and Helen and Tomasz in particular for this nice workshop. It's a second, for me, it's a second workshop in a row at SPICE. Last week, Rambert and I co-organized quantum spintronics workshop. There was actually quite a bit of overlap. Many people talk about antiferromagnets. Unfortunately, they couldn't stay for the second workshop. So there's also a quantum angle to this topic that so far may be secondary, but I think as time goes on, things will become more quantum. And for Sarah might talk about some quantum ideas. We've heard a lot about antiferromagnets being great for various things in spintronics as memory elements that could be switched, as sources of spin current, driven electrically via spin Hall effect, thermally via spin Seebeck effect. Also, obviously, and perhaps most naturally, they're terrific conductors of spin. So that has been mentioned already. And in this talk, I want to go over the spin conducting properties of antiferromagnets a little more systematically. The work was done, most of the work was done by my former postdoc, Sofa K. My current postdoc, Sek1, is continuing to work on these related issues. And these are the senior colleagues who will be collaborating, particularly the experimentalists, Amir, Drew, and Agent. I'll touch upon some experimental results by this gentleman. The antiferromagnet as a conductor of spin is a very old notion. So whenever you develop a theory of bulk dynamics and excitations in antiferromagnets, people have done at least half a century, going back at least half a century. The idea of spin transport is very natural so long as spin is a conserved quantity. In Heisenberg, in the most symmetric case of Heisenberg antiferromagnet, I should really keep track of because I elaborate too much. In the Heisenberg antiferromagnet, which are completely isotropic, all three directions of spin are conserved, so you could think of spin dynamics, all three components of spin dynamics in some hydrodynamic sense. In easy access or easy plane antiferromagnets, at least one component is conserved. And in this talk, because I'm interested in antiferromagnet as a carrier of spin, I will assume that at least they have at least one symmetry axis on which the spin is at least approximately conserved. What's new in this community specifically is not so much spin transport per se, but the various new ideas for injecting and detecting spin. So that's why a lot of progress has happened over the recent years. And particularly, at least three different classes of the techniques that people can use now to inject and very suppressively detect the spin. Normal metals, ordinary normal metals, typically with transformative interactions, can be used to inject the spin electrically and via spin Hall effect. So that is typically viewed as spin Hall effect producing some spin accumulation at the boundary, and that spin accumulation pushes the spin current in an antiferromagnet. Thermally, via spin Seebeck effect, you could drive spin current just by putting any ferromagnet next to the antiferromagnet. It doesn't even have to be metallic. And by thermal fluctuations, in principle, you could drive spin current. Perhaps there's an additional magnetic field or something, to define an axis on which the spin will be polarized. But when those ingredients are provided, then even just thermal fluctuations as in this conductive effect can drive spin current. Spin current can also be driven coherently by microwave driving. So one way to do it is to attach a ferromagnet next to an antiferromagnet and drive spin current by spin pumping, similarly to how spin current is driven by ferromagnets into metals. So I would say that probably a good summary for injecting spin and by reciprocity you could also detect spin in these 3 different ways. So that's as far as physics at the boundaries is concerned for injecting and detecting. Physics in the bulk, which is, like I said, is a bit of an older story. Perhaps one way to think about it, and that's the way we like to think about it, is in terms of 2 fluid dynamics. One, fluid in the sense that we have some conservation laws, and 2, one standing for coherent dynamics, LLG-like, and the other standing for incoherent dynamics mediated by the thermomagnets. So 2 fluid, in some loose analogy to superfluid dynamics in helium-4 mass superfluid. In some special cases, our 2 fluid dynamics actually maps couldn't be mapped precisely onto 2 fluid dynamics in mass superfluids, but I view it as a more general notion. You have always some kind of interplay between coherent and incoherent degrees of fluid. So that's what I refer to as the fluid, and in this talk I'll touch upon 2 fluid aspects. So to clearly separate between these 2 fluids, let's consider 2 special examples. Like I said, I need at least one symmetry axis to have conserved spin and degree of freedom. So the 2 simplest examples, which in some sense are really in the 2 extreme opposites of each other from the point of view of spin transport, are the easy axis antiferromagnets, such as the fruit fly of antiferromagnets, manganese fluoride, and the easy plane antiferromagnet. So one example of easy plane would be just a Heisenberg antiferromagnet subjected to an external magnetic field, which puts a nail bording into the perpendicular plane, and that effectively realizes easy plane. Or something like nickel oxide, when you have an easy plane defined by crystalline anisotropes. So in the easy axis antiferromagnet, we have 2 degenerate bands up and down, just like in some very loose analogy, 2 spin bands in a normal metal. H bar, well, spin is a good quantum number along the axis of symmetry. So we have 2 degenerate branches of excitations carrying a spin plus H bar or minus H bar along the symmetry axis. Very, very loosely, you could think of one branch living on one magnetic sublattice, other branch on another magnetic sublattice. Very, very loosely, of course it's not exactly true, but that would be a rough schematic of spin plus H bar excitation corresponding to one of the sublattice, mostly on the sublattice precisely. These thermal magnets can carry a spin current, just like electrons can carry spin current in metals. And for that, of course, at least for linear response type of spin current, we need to go to elevated temperatures larger than the gap. And then these materials can serve as spin carriers of incoherent magnets, much like normal magnets. So then you will have kind of 2-channel to develop 2-channel models, spin up and spin down, etc. At elevated temperature. So the spin current would freeze up at 0 temperature. The candid antiferromagnet story is a bit different and a bit more interesting. So in this cartoon, I'm showing a Heisenberg, simplest, most symmetric case of Heisenberg antiferromagnet. It's 2 sublattices, covalent sublattices, and subject to a external magnetic field. In the z direction, the ground state corresponds to 2 sublattices canted out of the plane, and then we have 2 non-degenerate spin wave branches. One that is gapless, corresponding to nail border processing in plane. That's the 0 mode, that's the Goldstone mode of this dynamic system, and a gap branch with the gap simply proportional to the external given essentially this Gaussian energy corresponding to the external magnetic field. the out-of-plane spin density, SZ, is canonically conjugate in this case to the azimuthal angle of the nail order parameter within the easy plane. And the dynamic description of the coupled SZ and pi dynamics mimics the dynamics of mass and phase in a mass superfluid. In particular, we have this Josephson-like relations for SZ being proportional to the time derivative of the azimuthal angle and the out-of-plane polarized spin current density Jz being proportional to the gradient of azimuthal angle. So in this sense, the spin current, again, polarized out-of-plane along the symmetry axis, is very much, its dynamics very much analogous to the superfluid. So the Gothard mode, linear dispersion Gothard mode is just a sound mode of the superfluid. And then focusing on physics at this low energies, near the Gothard mode, so neglecting this split of branch, we can develop theory of collective spin dynamics in very close analogy to superfluid, as has been pointed out back in the 70s by Son and 40 years later, he wrote a nice review article in Advances in Physics that, if you're interested in the topic, I encourage you to read. Okay, so the overview for my talk, I'll touch upon after this introduction on the three setups for exhibiting a spin current. So in an antiferromagnet, so the middle portion of the antiferromagnets, the contacts are whatever you're slapping on the antiferromagnets for injecting and detecting. In the simplest case, you would use something like platinum for injecting spin current on one side, detecting on the other side. And you could try to realize either the normal fluid or the superfluid regime for spin transfer gain between. In either case, you could use platinum and the same type of spin hole physics to inject and detect and spin current. Or you could have a kind of mixed setup in which one side is platinum, the other side is a ferromagnet such as YIG. And this setting you could inject a spin current, let's say a spin hole effect from here, and detect the torque by measuring line widths and damping like torque onto the ferromagnet as has been carried out in the experiment by our experimental colleagues in Japan, in Ono's group. Or reciprocally, you could drive kind of similar setup. In fact, this is a theoretical cartoon of a very similar setup of the experiment, except that the material recommended was nickel oxide, the experiment cobalt oxide, that was sort of similar. But the experiment is carried out in a reciprocal fashion. So ferromagnetic dynamics is driven in injecting spin current that goes through antiferromagnet and then detected by measuring inverse spin hole voltage. So this have become quite a standard setups for exhibiting a spin current through an antiferromagnet. And in this talk, I will, just because I don't have enough time, that's the only reason I will not talk about thermal effects, but also just as interesting, as I already pointed out. All right. Just to give you a very quick introduction and to give a flavor of the physics, the equations you would write down to put what I told you on solid footing. You started with Lagrangian. This is the standard, most minimal Lagrangian that describes bulk dynamics within an antiferromagnet, 2 degrees of freedom, M and the magnetization, which is very small, and N, which is nail orientation. So this is the simplest, so-called boring collinear antiferromagnet, which tends to be more complicated. And that's the minimal Lagrange. Just to give a rough idea, we have a kinetic piece that establishes canonical conjugacy between the magnetization and the nail orientated order parameter. We have stiffness of the nail order parameter. We have the small piece corresponding to a little bit of canting, and has magnetic stability, which is very small. Just you have to overcome exchange energy cost to come to some lattices, and we have some Zeeman term magnetic field coupling directed to a little bit of magnetization that might be present in the system. From this Lagrangian, you can get the equations of motions. In those equations of motions, you immediately see the conservation law for spin, and that's natural because this Lagrangian is isotropic. The spin current that you get out of the conservation law is very much like spin current that you would get for stimulant description of ferromagnet, which is given by stiffness times n cross the derivative, special derivative of n, projected on easy plane dynamics that gives you this superfluid-like expression for the spin current. The most important contribution to damping is associated with Rayleigh dissipation driven by the Néel dynamics, not by the magnetic dynamics like in the ferromagnet, by the Néel dynamics. So alpha Gilbert damping parameter, which is introduced as the coefficient in front of this Rayleigh dissipation function associated with the NLT, and gives rise to this angular momentum leakage term that takes angular momentum out of the system. So it enters in the equation of motion for the NLT. Just like the Gilbert damping, but on the left-hand side you have the N, on the right-hand side you have N cross the NLT. So that's the dominant damping process in the system. So it's still called the Gilbert damping. Now, that's the physics in the bulk. The physics at the interfaces, remarkably, is very much like in the ferromagnet. So we can still describe the angular momentum transfer at interfaces using the spin mixing conductance type of description. So I'm saying it cryptically, but I think most people understand what spin mixing conductance is in the context of ferromagnetic spin transfer. So in antiferromagnets, in fact, any magnetic material with collinear order, the same spin mixing conductance phenomenology carries through. So long as the low energy degrees of freedom correspond to essentially rigid directional dynamics. At energy scales much less than the exchange energy, I can neglect, for the purposes of this interfacial spin transfer, I can neglect the internal dynamics of this kind, just follow and focus on the rigid dynamics, and then for any rigid collinear dynamics, this spin mixing phenomenology is operative, just like in the ferromagnetic case. So we have this definition. I'm basically borrowing what we know from the ferromagnetic normal metal interfaces. The same definition of the mixing conductance, the up-down stands for up-down along the order parameter, collinear order parameter, and that's the full expression for the spin current at the interface. This expression is relevant both for spin Hall and spin Zebek type of physics. I have, let's focus on this piece, the main, the dissipative piece that's most important in practice. And the coefficient is the real part of this mixing conductance, and we have this expression m cross mu cross n. Mu is effective bias across the interface. This effective bias is given by the difference between spin accumulation on one side that corresponds to the torque, and that is dynamic piece associated with the directional order parameter dynamics on the right-hand side. That's the reciprocal pumping. Now, the only question in comparison to the ferromagnets is what is the value of this mixing conductance? Maybe it's 0. Can it be as large as in ferromagnets? So the answer is that it's generally non-zero, and generically we expect it to be just as large as in ferromagnetic interfaces. So roughly one quantum channel, basically one e square over h per quantum channel. Roughly speaking, one per interfacial atom. So roughly, in practice, that means between 10 to 18 and 10 to 19 meters square in the dimension is units. So, okay, and then the reason why this mixing conductance is non-zero generically is because you have, even in the most pessimistic scenario, when the interface is magnetically compensated, you have a phase shift between up and down reflection coefficient in the umplot scattering channel. So naively you might think, okay, It's an antiferromagnet. Roughly up and down reflection coefficients are the same. So that means that the mixing conductance will be 0. So essentially, like it's visible small magnet. Because of the phase shift between up and down in the scheduling the loop-up channel, you do get non-zero mixing conductance. And even in the perfect case, the dominating by the loop-up schedule, the moment you sprinkle some distorted, it opens even more channels for the mixing conductance. So generally, we expect it to be just as large as ferromagnetic case. So that's it. It's an interface. That means the antiferromagnetic interfaces are just as receptive to spin currents driven by spin Hall or spin Z as ferromagnetic interfaces. Okay, so now equipped with this understanding what happens in the bulk, what happens in the interfaces, we can start developing circuit-like descriptions for spin currents flowing into our material at interfaces. This is propagated through the material according to the standard reflection theory of the dynamics of the appropriate material, and then exiting some other interface by reciprocal process. One example of such a simple simple spin current circuit in antiferromagnetic heterostructure again exploits this idea of superfluidity. So you have an easy plane antiferromagnet attached to leads, and very much an analogy to our proposal for the similar ferromagnetic superfluid transport. We have in the geometry the whole fact that using spin conduction out of plane, it enters the superfluid dynamics of antiferromagnet through this mixing conductance physics parameterized by the mixing conductance on the left interface, and then you have propagation of out-of-plane spin density conjugate to the planar nail dynamics across. There's leakage of out-of-plane spin density into the lattice parameterized by the Gilbert damping parameter as defined a couple slides ago. That physically corresponds to mechanical torque on your sample holder, and then whatever has not been leaked according to the Gilbert damping, it is emitted at the right and in proportion to the mixing conductance of the right interface, and could be detected by inverse spin Hall voltage. So experimentally, that could be detected here as a non-local drag effect, or if you're driving currents at both ends, magnetoresistance, some local magnetoresistance. So that's a circuit. We have impedances of the interface with the mixing conductance, effective impedance for the leakage of diagonal momentum into the substrate proportional to the Gilbert damping. The net final results for the frequency of nail precession in the steady state. This is a DC setup. It's proportional to the spin accumulation induced, let's say, with the spin Hall effect at the left, and this expression that reflects how the spin current is partitioned in and out of my antiferromagnetic channel. And the spin current emitted at the right side is given simply by the frequency of precession times the mixing conductance at the right side. So this is a pump spin current pumped by antiferromagnetic nail dynamics measured on the right and within the inverse spin Hall effect. So just to give you more details about the schematic, but again, the story, for those of you who've seen the story of ferromagnet, is essentially identical. That's our, for example, top view. This is our superfluid conductor, which is based on antiferromagnetic insulator with nail order processing within the plane, and putting the numbers just to estimate the magnitude of the effect. So the spin Hall angle for platinum taken to be 0.1, mixing conductance taken to be the same as the Yick platinum mixing conductance, and we can estimate the drag coefficient over a micron long antiferromagnet to be at the level of 10%, which is gigantic for a drag, such a non-local drag effect. So it's not that it measures this, it's pretty unambiguous, very clearly distinguishable from things like hormone drag, etc. Okay, now one could refine this setup and try to separate the effects due to dynamics and texture of the nail or the parameter. In particular, if we're interested in the effects due to the texture of the nail or the parameters, for example, you wanted to induce the static texture by these torques at the boundaries, and then study how the texture is stable, or utilize the texture for something that I'll explain on the next slide. We could go to this geometry. So we would be sending passing electrical current in parallel at these two ends. So then the spin current is, by the spin Hall effect, is injected at the left interface and then detected and drawn out at the right interface in a symmetric fashion. So then we will have the same torques at the two boundaries, which will twist the nail order into a static texture, so there will not be leakage due to the Hilbert damping. So that realizes a persistent spin supercurrent without any dissipation. And that would be perfectly stable like any supercurrent, barring phase slips. So this would be a geometry to study magnetic phase slips in the plane texture of the nail or the parameter. Those phase slips would be thermal or quantum. The thermal phase slips are the same as in the ferromagnetic case. This is always story for ferromagnets, and the classical antiferromagnets really coincide. But in the quantum regime at very low temperature, the story for the phase slips and antiferromagnets is different from ferromagnets. So it's very nice post-Lestaulas type of physics that you could study if you go with this geometry to low temperatures. Amazingly, so that I don't have time to go into this into detail. It's a paper that you could study if you're interested in this topic. But I just want to emphasize that the physics is really, the underlying physics is on the one hand very interesting. On the other hand, directly accessible with the standard measurement techniques, just like I described. So all you have to do is measure magnetic resistance of this type of circuit. And it is ordinary magnetic resistance of two platinum wires sandwiching an antiferromagnet. Whatever phase slips, whether thermal or quantum, that would be taking place in this antiferromagnetic layer, and you could then detect through magnetic resistance of platinum at low temperatures. So I think it's a fascinating tool to study low temperature physics, even quantum fluctuations, well, as well as thermal fluctuations, but most interestingly, quantum fluctuations for antiferromagnets, whether it's simple or more interesting. Okay, that's it. I'm going to skip the last part, unfortunately. Let me stop here. Thank you for your attention.
How is sensitive to your results? So is it important to start from the nail state, not from the quantum state? What will happen if you start from the quantum state?
Sorry, I don't understand the question.
I mean that at T0, an antiferromagnet could be in a quantum state, not in a nail state.
I'm sorry, I don't understand what you mean. Obviously, this is not the classical up and down state, quantum fluctuations.
It's not classical, but a tangle state.
Okay, first of all, what dimensionality? 1, 2, 3, and let's. Well, in 3 dimensional, it's just an ordinary nail state with some quantum fluctuations on top of it.
Okay, so the second question. You showed that this twisting of the phase is related with a mechanical moment.
No, the dissipation of the dynamics would dump angular momentum into the mechanical degrees of freedom.
Yeah, so you have also magnetic mechanical rotation, so the momentum in the system.
Yeah.
Is it possible that instead of twisting phase, you twist the sample mechanically in this case?
Are you alluding to the magnetic-elastic effects? Yeah, so I have obviously disregarded all the magnetic-elastic effects, perhaps like what we've been discussing, maybe either I don't have those effects to start with, or I go to granular materials and I want to average out all those magnetic-elastic effects. But what exactly are you interested in with respect to?
I mean that you show the scheme when you have a sample and you fix, you measure something at left and right side. So if you fix your borders, then this mechanical moment can produce a kind of stress which removes all these phase effects.
Well, I mean, the reciprocal of this twist is, so, this twist is just, which one? The Barnett, the Einstein and the Yaroslav effect. So the reciprocal would be the Barnett effect. If you start oscillating things, it would be just some effect of magnetic field in the frame of reference. I mean, there are reciprocal effects to, to this leakage of the element. I don't think that interesting or strong. Some small effect of magnetic fields with respect to the rotating sample holder. But we haven't pursued that line, yeah. It's because some inelastic effects are very interesting in their own right. We're focused on the simplest case, which is interesting enough, and then one can build upon.
So when you talk about superfluid reductions, can you say when you don't time what the general digital argument why superfluid conductors with interface with Antiferromagnetic is more or less the same as
So the mixing conductance for any collinear ferromagnet doesn't even have to be two sublines. Any collinear magnetic order parameter would be defined in this fashion. Okay, well, up and down, these are reflection coefficients for electrons coming from the normal side, with up and down standing for the direction along which you form the order, magnetic ordering. So now the question is, well, if the insulator is non-magnetic, then R up and R down are the same, and then this boils down to lambda Buriga conductance of an insulator, which is 0. The moment you have if you have something like antiferromagnet, if you have a ferromagnet, then R up and R down are different than you have mixing conductance. If you have something like an antiferromagnet, so there's no net magnetic moment. R up and R down, in some sense, on average, the magnitudes are the same. But there's a phase shift between that. And that phase shift, you can easily see for this, let's say for this, it's just a proof of principle. Simple model. You see this phase shift in the Umlaut channel. So in this backward channel, the reflection coefficient is the same. In the Umlaut channel, the reflection coefficient is exactly pi phase shift because of let's say doubling of your brilliant zone by the magnetic order. So the Umlaut precisely introduces the pi phase shift. So it flips the sign in this term, and that's why. The mixing conductance is determined by the sketching into the Umlaut channel. But the moment you sprinkle this order, there will be more terms, and you get that's always positive in mixing conductance. The moment it's not 0, it's positive because it's a distributive coefficient, cannot be negative.
Yes.
So many of the interfaces that you're describing might have strong interfacial spin coupling. It's not really spin flip scattering, which is included in the mixing conductance. How do you think that would affect?
Yeah, so then we deal with that in exactly the same fashion that we deal with, like we deal with spin modifying. So then we just lumping all the spin orbits. So long as it happens at the interface, whatever physics that happens at the interface, we're just lumping this spin mixing conductance. This is just an illustration that the spin transfer happens. In a practice situation like you mentioned, we're lumping all the physics into some torque terms. So we define spin effective spin Hall angle that is some convolution of this mixing physics and this spin orbit physics. So there's a systematic way to do it. And then later on I'm using, for example, platinum for spin injection. I'm parameterizing the value by some effective spin Hall angle at the interface.
That is stated because it's an optical parameter.
It's a very well-defined phonological parameter that could be measured and people can calculate it, but of course not by this expression, it's something more complicated.
Exactly, regarding this question of how would you expand in terms of a counter system?
So again,
how would you expand this even for a non-collinear case like a counter?
For the non-collinear, well, good question. Like a system that could be described by not by direction but by like rigid body type of rotation. Yeah.
Well, or a two-counted surfaces. Two-counted surfaces with a finite angle.
Oh, two-canted. Well, again, if the system is the basic material is an antiferromagnet, I don't think this canting is actually important. It's not going to change.
No, in the general case.
In the general case, so then I would have to describe my other parameter more like a rigid body than a direction. So we haven't, the simple answer, we haven't thought carefully about it. Yeah, but that's a good question that would be pursued using the same philosophy, but it will have more parameters. It will have more parameters associated with this dynamics. So just it's a question.
Can you make a comment on this G-type antiferromagnetic is not more manipulation around the band?
Can comment on what again?
For G-type antiferromagnetic around the band, there is much more reflection around the
I'm not sure what exactly you have in mind. What kind of deflection? What are you talking about?
around the band or the
Like, yeah.
G-type antiferromagnetic, you have much more solar
The reflection of what? Like the electrons? Okay, I didn't, honestly, maybe we should talk about that offline. I'm not sure exactly what the issues are there.
Okay, let's thank Yaroslav again.